Hello, I'm Mir Hamidul Hussain. Have you ever thought how your device like laptop, smartwatch, or mobile phone runs so fast using small battery? Behind the scene, there is a very interesting electronic device, which is a MOSFET that actually runs the today's modern life. So in this video, I will talk about the MOSFET. And before we start, let me tell you the things I will cover in this video. First, we will see the construction of real MOSFET, and then we will explain about the operation of the MOSFET, and then I will discuss about the IV characteristics, and then the different operating modes uh, will be discussed in this lecture. MOSFET means metal oxide semiconductor field effect transistor. Here you can see the symbol of a MOSFET. There are three terminals: drain terminals, gate terminal, and source terminals. And in hardware lab, you will see like this type of component, which also have three terminals, and this one is gate terminal, this one is drain terminal, and this one is source terminal. The physical structure of this MOSFET is like this figure. Now we will see the basic structure of a MOSFET. First, we'll take a material which is silicon base or parent material. Then we will dope with a trivalent impurities to make it p-type substrate. And there are two n-type wells here. Out of these two wells, one will act as a source and another one will act as a drain. And this black part is actually a metal contact, and there are four terminals. As you can see, this terminal is source terminal, this one is drain, this one is gate terminal, and this one is body terminal. Point to be noted that the gate terminals and the p-type substrate are not directly connected. Here is a thin oxide layer which is made of silicon dioxide, which is also known as gate oxide. This layer will act as a dielectric material. As we already know that in a p-n junction, a depletion layer is formed. Here you can see the depletion layer, and uh, you can see that there are four terminals, but the body terminal and the source terminal are internally shorted. So three terminals are left: one is source, one is gate, and one is drain. This part of the MOSFET can be considered as a capacitor. As we know that capacitor is nothing but a two metallic plate separated by a dielectric material. Here you can see this metallic plate or gate is a conducting material. P-type substrate is also a conducting material, and this gate oxide layer will act as a dielectric material. So this can be compared to capacitor. Now, if we increase the gate voltage with respect to the source and source or body, then the positive charge will start to accumulate near the gate terminals, and this will push down the majority carrier, which is whole of the p-type substrate, and the minority carrier of the p-type substrate will start to accumulate here. If we increase VGS further, the negative immobile ion will be uncovered and take place here. And now this is how the channel is formed between source and drain. And this occurs when when the VGS is greater than or equal to a threshold voltage VTH. So the channel is now ready to allow the flow of current, but no current will flow from source to drain. Here I have to mention another thing. This channel is N type, and there is another MOSFET where the channel is P type. So that MOSFET is known as p-type MOSFET. But in this lecture we will learn about the n-type MOSFET, and this is known as n-type MOSFET because the channel between the source and drain is n-type. Now the channel has already been created, but no current will flow from source to drain because there is no potential difference between the source and drain. As you already know, current flow from one terminal to another terminal if there is a potential difference between between the two terminals. Now let's see what happens if we make a potential difference between the drain to source terminals. Uh, if we connected the drain and source terminal with a voltage source, then electron will start to flow from the source terminal to drain terminal. We already know that the direction of the current is opposite to the flow of electron. So so the electron will flow from the source to drain, but the current will flow from the drain to source. So the current will flow around this path, and this current is known as drain current or ID. If we increase VDS, the drain current ID will increase. At When the VDS is small, the relationship between the drain current and the VDS is linear. Uh, that means the drain current ID will increase linearly with the VDS. But if we increase VDS further, the channel on the right side will get narrower, because if we increase VDS, the voltage drop across the channel on the right side will reduce. As you can see, the voltage drop of the channel on the left side is constant, but if we increase VD, the VGD will reduce, because VGD can be represented as VG minus VD. If we increase VDS, VD will increase and the VDS will decrease. So the channel voltage drop across the channel on the right side will decrease if we increase VDS. If a channel, here you can consider the channel as a resistance. So at first the resistance of this channel is constant, but if we increase VDS, the width of this channel on the right side will get narrower, so the area of this channel will reduce. So as you know that the resistance of a channel is inversely proportional to the area of this channel. So if if the area of this channel reduce, then the resistance of this channel will increase, and thus the current flow between the source to drain will decrease. At some point the channel will the channel is on the right side is a point which is known as a pinch off point, and this occurs when the VDS is equal to the VGS minus VTS. VGS minus VTS is known as overdrive voltage. If VDS becomes or equal to the overdrive voltage, then the channel on the right side is nothing but a point. If we increase VDS further, then this pinch off point will shift toward the left side. And in this and here actually the current flow from the source to drain will be saturated. So if we increase the VDS, the value of the current will not be increased. The current will flow at a constant value regardless of the change of the VDS. Now we will see the IV characteristics of MOSFET. First, we will see how it works when VGS is less than the threshold voltage. If VGS is less than the threshold voltage, no channel is formed between the source and drain, so no current will flow from source to drain. So this will act as an open circuit. Here you can see this is the actually IV characteristics of a open circuit, and this region is known as cutoff region. Now if we increase the VGS greater than a threshold voltage, Let's assume VGS is equal to 5 volt. Then if we increase VDS or drain to source voltage, then the current or the drain current will start to flow from source to drain. For a small value of VDS, the drain current will change linearly with VDS. So here you can see this IV characteristics looks like an IV characteristics of a resistance, and the relationship between the IDS and the VDS is linear. But when we increase VDS further, the width of channel reduce, the area of channel reduced, and so the resistance of this channel increases. So ID will also decrease. So in this part, the relationship between ID and VDS is no longer linear. At some point, the current will be saturated, and this occurs when the drain to source voltage is equal to the overdrive voltage or VGS minus VTS. And here you can see, then if we increase the VDS, the current will not change, the current will be saturated. So the left side of this graph or this IV characteristics is known as triode region, and this is also known as ohmic region, and right side of this graph is known as the saturation region. Triode region occurs when the drain to source voltage is less than VGS minus VTS, and the saturation mode occurs when the drain to source voltage is greater than the overdrive voltage or VGS minus VTS. So here we can see there are three operating modes of a NMOS. One is cutoff region or cutoff mode, another one is triode mode, and another one is saturation mode. This is the end of this lecture. Thank you for your attention.